Now let's talk about the concept of active contours, also referred to as snakes, a very powerful tool for finding the boundaries of objects in an image. So first, let's take a look at what is an active contour. You have an image here of a coin, very simple object, and what you have drawn around it is an initial contour. This could even be hand sketched. And what you want this initial contour to do is to evolve over time so that finally it goes and latches on to the boundary of the coin itself. That's what an active contour does. Like so. And so an active contour iteratively deforms and the initial contour so that it ends up near the pixels on the object that have high gradient or edges, which would be the boundary of the object generally speaking. And you also want to make sure that the contour that you end up with doesn't have knots and twists in it, that it's smooth. So active contours are also referred to as snakes, very popular in many domains, in particular in fields like medical imaging. One of the powerful things about these contours, these deformable contours, is that you can use them to track objects over a video sequence. So for instance, if you're able to find the contour in the first frame right here, which would be this thin, faint red line that you're seeing around the lips, then that can be used as the initial contour for the next frame, and therefore very effectively track the boundary as it deforms over time. Or for that matter, if you have an object and your view of that object is changing, in that case as well, you can start with an initial contour and simply use that to track it over subsequent frames. That makes it a very powerful technique for tracking as well. So your first step is to represent the contour itself. This is very important, the way you do this. So here is a contour, and let's say we want to represent it with n points, and we call these control points. And initially, the sampling of this contour is uniform in that the distance between consecutive points is fixed. So it's straight lines of fixed lengths between consecutive points. So now, we need to somehow take this initial contour, which is sitting around this object, in our simple case, the coin, and we want to have it actually drawn in to the object itself. You need some forces, something that makes it evolve over time and come closer to the object and latch onto it. So the obvious thing to do is to apply forces, if you will, to this contour, where those forces actually depend on the gradient of the image. So if you apply the gradient operator, the del operator, if you remember, take the magnitude of that and the square of that, that could be a good trigger or a stimulus for the contour to react to. So that's what we do here. We take the gradient magnitude squared, that's what you're looking at here. And now the question is, how do you attract this contour closer to the object when the gradients are sitting so far away? So the trick here is to actually blur the gradients. So if you blur the gradients, you get this. And by doing so, you're actually creating sort of like a force field or a potential field so that even when the contour is sitting far away, it is drawn towards it. As long as it's in this field, it's drawn towards the boundary. So here you see the blurred gradient magnitude square. And now what we want to do is to make sure that we draw the contour towards the object, which means we want to maximize the sum of the gradient magnitude squares. So ultimately, wherever the contour ends up, if you take all the control points on the contour and you sum up the square of the gradient magnitude at those points, that should be a maximum. And that's the goal here, and that's how we are going to evolve the contour. So maximizing this is equal to minimizing the negative of the same thing. And the reason we play this trick is because later we are going to use other terms. We're going to add other terms to this problem, which we want to minimize. So we want to minimize all the terms. And so we do a maximum of the sum of the gradient magnitude square. And this can be written as follows. We'll call it the image term right here, and that's the sum over all the control points of del. This is a Gaussian that you've applied to blur the magnitudes, convolved with the image itself, and you're computing the magnitudes at these control points. And that's squared. So that's the gradient magnitude square, which is written out here, summed over all the control points. Okay, so now we can develop our first algorithm using this idea. It's a greedy algorithm, very simple algorithm. And here's how it goes. For each contour point, Vi, we are going to move Vi to a position within a small window. Say this is a window right here. Within this window, we're going to move Vi where the energy function E image for the contour is minimum. So we're going to take a greedy approach in that we're going to do it for this control point, and then we'll move to the next one, and the next one, and so on. And that would give us the next iteration of the contour, and then repeat this process. So if the sum of the motions of all the contour points is at some point less than a threshold, then we're going to stop. So that means that you get to a point where the contour doesn't really move anymore. If it's still moving, then you go back to step one. That's it. That's your simple algorithm, which works reasonably well. It has some problems, as we'll see, but it works reasonably well. The one thing to bear in mind is that because this is a greedy solution, you're not guaranteed to get the optimal result, in that you're doing this sequentially, control point by control point. And it can also be somewhat slow for fairly large contours. So here's the way it works for the object that we were looking at. And let's say that the image itself has some noise in it. And so, yes, by and large, it ends up latching onto the coin. But you also see that towards the end, that there are control points that are actually latching onto some of the noise in the image right here. And you see these sudden twists and turns in the contour. And those are things we want to get rid of. In doing so, we would make it less sensitive to noise and less sensitive to the way that the contour itself is initialized. So we want to add more constraints that makes the contour contract and remain smooth. In other words, we want to add constraints that make the contour sort of behave like a physical object with certain properties. So one of those properties is elasticity. We want it to behave sort of like a rubber band. That is, it's going to be pulled in. Now remember, you can also do the opposite. You can behave a contour also balloon out, but that's just a little simple trick that we play, very small change. But for our purposes here, we're going to look at the elastic property where it actually behaves like a rubber band, it contracts. So it should look something like this. If these are control points, the rubber band should go something like that. And you want it to be smooth. Act like a metal strip. When you bend it, you're not going to have any sudden twists and turns. You want it to be smooth. So we want to add these constraints to the previous formulation. So these two constraints, if you take them together, you're really computing the internal bending energy of the contour. If you were thinking about it as a physical object made of physical material, you're actually minimizing the internal bending energy. That's what you want to do. And we'll call this term the contour term. And that's going to be alpha times the elastic term plus beta times the smoothness term. You can adjust alpha and beta based on your application to trade off elasticity for smoothness and vice versa. So now let's see how we can formulate these two terms. What are these two terms? Well, so let's say that we'll go to continuous domain. Let's say we have a continuous contour that looks like this. We'll soon discretize it, but for now we'll do it in continuous domain. And that's V of S. And that has, of course, two coordinates, X of S and Y of S. S is the parameter, and let's assume for a minute that S goes from 0 to 1. So if you take any point here, what you want the elastic term to do is to make sure that the change at that point is minimized, meaning to say that the first derivative of v with respect to s is minimized. So we take the square of that here, but the first derivative, we want to keep it as small, which means we don't want the point, the contour to stretch too fast. From one control point to the next control point, we want those segments to be as small as possible, and that makes it contract, like a rubber band, right? And the smoothness term uses the second derivative of v with respect to s. And what that means is that if it moves from here to here in the first step, and then from here to here in the second step, we want to minimize the difference between these two vectors. That is, the rate of change needs to be minimized, and therefore that keeps it smooth. And that's why we take the second derivative of v with respect to s, and we square that as well. And we know how to compute this using finite differences in our discrete case. So if you're looking at the control point vi, we know how to compute the elastic term for vi, which would simply be vi plus 1 minus vi, that distance squared. We know how to express that in terms of x and y. And we also know how to compute the smoothness at vi, which is a second derivative, which would be the difference of the difference. So it's vi plus 1 minus vi minus vi minus vi minus 1, that difference squared. And so that can also be expressed in terms of x and y. So we know how to compute it at any given point on the contour. And now what we want to do is to compute it for the entire contour. So the bending energy for the entire contour is alpha times the elastic energy plus beta times the smoothness energy. And that's being computed here as the sum of what we derived in the previous slide for a single point over all the points, and again over all the points. So now we're going to combine all of these forces, so to speak. Which are the forces? We have our internal bending energy that we just discussed. That's the contour energy. And the image energy that we discussed previously that was based on the gradient magnitudes. So that's the total energy of the active contour. And we want to minimize the total energy. So now let's again come back to our greedy algorithm. What we do is we uniformly sample the contour to get n contour points. Now this seems like a minor technicality, but this is a very important point. We're going to come back after each iteration and uniformly sample the contour, again, to get these n points. If you don't use that term, you're going to go off in a weird direction. You need to do that uniform sampling again for each iteration. So now you've uniformly sampled it, and now for each contour point, we are going to move vi, the position of that contour point, to a position within a small window around vi. Let's say this is vi and this is the window w around it. We're going to move vi where the energy function E total this time, which is the sum of both the image term and the contour term, is minimum. And we're going to repeat it for all the control points, and that gives us the new location of the contour. And we're going to check whether the motion of the contour points is large enough to continue. If it is really small, then we stop right there. If it is continuing to move, that is, there is enough change in the contour itself, you go back to step 1. And repeat, keep going. So let's see how this works, and in particular compare it with our previous scenario of not using the bending energy. So here on the left, you see it, you see how the algorithm works by just using the image term. So there is no contour term right here. And you see the problem that we had in the past, which is you end up getting these knots right here. And that's because noise begins to pull at the contour, and actually it ends up getting stuck in these places. Whereas here, you end up with a very nice result. It's more resilient to noise, it's smooth, and it contracts and latches onto the boundary of the object. Now what happens if you have two of these coins? Well, it actually behaves sort of like a rubber band. This is the active contour you end up getting. And of course, you still have these, the image term pulling you further in because you have gradients in this part of the coin and right here on the inside. However, because you have your elastic term and your smoothness term, you end up converging at in this particular contour right here. And you can also think about how you can adjust alpha and beta to change the behavior of the active contour. In this case, you have something with a larger alpha, which makes it behave more like a rubber band, more elastic. And you see that it ends up here. It doesn't actually go in too much. Whereas here it is a smaller alpha, a little bit less of a rubber band, and therefore it's more influenced by the image term, and the gradients are pulling it in a little bit more. Okay, so now a few comments related to active contours. So the first thing is that you can modify this formulation in many different ways. Firstly, you could, while you're doing this, also add an extra term that penalizes the deviation of the contour from a prior model of the object. Let's say you had a pretty good idea of what the object actually looks like, its boundary. You can add that term in there as well, so that finally whatever result you end up getting not only satisfies all the constraints that we have introduced thus far, which is the image constraint, the gradient constraint, and the contour constraint, but also there is a prior model constraint. And then one issue with, which you may have guessed, with the contour is that it needs a good initialization. If you end up with a contour that's really far away, that is, you start with a contour that's really far away from the real object, it's going to be very hard to create a force field or a potential field that's able to draw it in. It's very likely that it'll get latched onto other things in the image. And finally, as I mentioned earlier, we have these contracting forces, these elastic forces, rubber band forces in our current formulation, but you can imagine that you can replace it with ballooning forces. That is, if you have an object, you can define a contour inside the object, and the whole idea would then be to actually balloon this contour so that it goes and latches on to the boundary. That can be done with ease. So let's take a look at a couple of examples. This is an example from medical imaging. You have I think it's a scan of the skull here, the head, and you have this very thin, faint line, which is your red boundary, and that goes and latches on to the boundary of the object itself, and it does extremely well. You can see that the line actually twists around here and it goes around this part, and so it's a fairly complex boundary, but yet it's able to latch onto it. And by the way, this has also been used for what's called interactive image segmentation in tools like Photoshop. This is magnetic lasso tool in Photoshop, and you can see here that a user is simply using their cursor to roughly outline an object, and the active contour of the snake is latching on to the actual outline of the object.